Hi, I'm David Wolpert, and I wanted to talk a little bit today about my solution to the Riemann hypothesis. The Riemann hypothesis is a problem that's been considered kind of the holy grail of problems in the mathematical world for the last 200 years. So, what it is that you have a zeta function is equal to a summation of 1 over 2 plus 1 over 3, and each one of them has a exponential term of s. Now, s doesn't necessarily need to be the real numbers. So it's in the complex plane. And what the Riemann hypothesis says is that if there are zeros that are non-trivial, which are the trivial zeros, are on the x-axis, then they will all fall in the line of 1/2. Now, I studied this problem in depth in about 2017 when I was looking at the summation notation for the exponential function and the natural numbers. So the natural logarithms as well. And I realized that this was already done, but it was newer to me. So it was the decomposition of the uh, Riemann hypothesis using what's called Euler's equation, or Euler's substitution, where you have an exponential to an imaginary number, and that becomes a term in the complex plane that can be represented. So I started looking at it from that and started to play around with it using just Word and created notes. And what I found was that for the terms to be true, the term of e to the theta, which is the would be the first term in the uh, in the summation, and e to the theta plus beta I, where beta I is the representation of the complex number, can be broken down so that you can factor out a term of e to the theta from the subsequent summation. And so what you have is that in the complex plane, the two portions of the complex number have to cancel out in some way. And I realized that there is this oscillation as it approaches a zero, where you have this corresponding terms that approach zero through cancellation. And it's kind of an interesting problem. And I wrote up my notes on it in 2017, had them notarized because I felt I was on to something. Through the trigonometric identities and through the uh, factorial functions, I was able to come up with a hyperbolic term and a symmetric term. So it's called meromorphic term, where one side of the graph is the same as the other side of the graph. Typically, in the past, we would do what's called analytic continuation, where we say, well, the graph kind of approaches this number from the positive direction. We're sure about that. And it appears that it should approach it from the negative direction. But what I found out is that if you have zeta of s and you multiply it by zeta of negative s, you can come up with some terms and come up with a reasonable functional analysis that can come up with an analytic continuation without having to rely on analytic continuation. Now, this is important because as I approach the problem from a perspective of trying to eliminate zeros outside of the half line, as opposed to saying that there are zeros on the half line, it became important to note that as I looked at places where the critical strip is from 0 to 1, which would be the strip from 0 to 1, all the complex numbers. And what this eliminates is that as you come from different directions, there can't be zeros. And I knew that, but I tried to figure out how I could show that without having it approach zero at a relatively um, indeterminate fashion, because even if there's one zero that's slightly off of that 1/2 point, that breaks the Riemann hypothesis. So what I did was I used trigonometric identities in order to reconstitute the terms into something a little bit more reasonable, so that I could look at where the terms approach infinity and show that there's a continuation to infinity, and that those poles in an infinity in the trigonometric terms can be reasonably accomplished. And that gives us the points at which no zero is off of that critical line. This is important. This is an important problem. And it's something that I have been working on for 9+ years. And what I decided to do is to use the inverse function, not the inverse, but it's the reciprocal function, and be able to reconstitute the terms in hyperbolic functions. And it shows that there is no zeros anywhere else on the plane except the trivial axis and the 1/2 line. And this is exactly what the statement of the Riemann hypothesis was. And so by transforming these terms using infinite numbers and U theory, fractal geometry, and being able to come up with substitutions from trigonometry, not even, they're not that complicated of terms in order. It's a lot of substitutions from well-known things, including the Pythagorean theorem. And this gives us the tools that are required in order to solve what is considered one of the hardest problems in mathematics. So I would say to all of you, it's important to remember that these terms are things that you learn back in high school. So it's kind of interesting that those high school mathematics can be applied to the most difficult problems that we've ever seen. Now, there is a parable that I like to say along with this, which came from this idea of symmetric functions, which is, if you have a term y to the fourth, how would you expand that? Well, y to the fourth can be expanded as y times y times y times y times 1. And if we took one of those y's away, it's just y times y times y times 1. And if we took another y away, it's y times y times 1. And we take another y away, and it's y times 1. And we take another y away. There's no more y's left. There's still 1. So even when it seems like there's nothing there, there's 1 in everything. And that came about through thinking of this exponential term as a variable. And when you start to develop skills, and especially toward calculus, you want to be able to vary variables by small amounts and kind of get a feel for what is happening in the equations, so that you don't just have a put into a calculator, hope you understand what the number means, or have an answer and not really understand what the number means, but to have a genuine feeling that you are confident in how things behave in mathematics. And that's something that's important for everybody to learn and develop if they are using mathematics on a regular basis. So, this was just a little bit of a talk. Again, I'm David Wolpert, and thank you for listening.